Hi everyone, in this video I'm going to talk about our latest work on learning to weight samples for dynamic early exiting networks. In the deep learning era, as the performance of deep networks generally increases together with their computational cost, people are paying more and more attention to the trade-off between accuracy and efficiency. It is known that in the conventional inference procedure of a deep network, all the layers will be activated sequentially for all input samples. Our work focuses on a special type of dynamic neural networks, named dynamic early exiting networks. When processing an easy input sample, it can exit at a certain early classifier if the classification confidence of the classifier exceeds some threshold. When the prediction result of this sample is output at the early classifier, all the deeper layers will not be activated, and the computation could be saved. In this way, dynamic early exiting networks have achieved very promising results in better trade-off between accuracy and efficiency. In such dynamic early exiting networks, it is obvious that different exits will handle samples with different complexity at the inference stage. However, most existing researches focus on the architecture design of multi-exit networks, and they mostly adopt the same training objective as static models. Here we ask a question: is this training objective optimal to dynamic early exiting networks? We believe that the answer is no, because the conventional methods treat all training samples equally in optimization, which leads to a gap between training and testing. Our motivation is that training samples with different complexity should contribute differently to the multiple exits in dynamic early exiting networks. To bridge the gap between training and testing, our basic idea is learning to weight the training loss for different samples at each exit. In this way, different samples could be emphasized by different exits in training. Here we give some notations and formulations. Specifically, we use F to denote a multi-exit dynamic network, and Fk is the kth subnetwork containing the kth exit. As mentioned before, the traditional training objective is the summation of the cross-entropy loss at all exits. In contrast, we weight the loss of each training sample at each exit with W. This weight is predicted by a weight prediction network. For each training sample, the weight prediction network takes the loss from all exits as its input and directly predicts the loss weights at all exits. We denote the weight prediction network as G, and its parameter is represented as theta g. Okay, now we have two models to optimize. One is the classification network F, and the other is the weight prediction network G. Inspired by MetaWeight we propose to use meta-learning to jointly optimize these two networks. Here is the overall training pipeline. In each training iteration, we first use the current G to produce the loss weights, and use the produced weights to perform a pseudo-update for the classification network F. Then we use the pseudo-updated F to update the weight prediction network G. Finally, the updated G is used to produce the new weights, and F is updated using these new weights. Note that in this meta-learning framework, we reuse the training dataset as our metadataset, rather than using a standalone metadataset as in MetaWeight. We can analyze the gradient flow for optimizing these two networks. The first step is forward propagation and calculating the loss from all exits. Then, we use the weight prediction network G to produce the loss weights, and use the weighted loss to perform the pseudo-update for F. After that, we need to mimic the dynamic early exiting behavior on the metadataset and allocate the metadata to different exits. Next, we calculate the classification loss of each exit on its allocated data and construct the meta-objective to optimize the weight prediction network G. To summarize, there are two training objectives. The first is the weighted cross-entropy loss, which is used to update the classification network F. The second is our proposed meta-objective, which is constructed by aggregating the loss from each exit on its allocated metadata. This meta-objective is used to optimize the weight prediction network G. Our algorithm is a general training method, which is effective on different multi-exit models, including MSDNet and RANet. We conduct experiments on different datasets and compare our method with other training techniques. Here are our main results on the large-scale ImageNet dataset with the MSDNet architecture. It can be observed that with our training algorithm, a better trade-off between accuracy and efficiency could be achieved. These are our results on the CIFAR-10 and CIFAR-100 datasets. We also compare our method with other training techniques and validate our method on another representative network architecture, RNet. We conduct extensive ablation studies to validate the effectiveness of different design choices. Finally, we show that our method is also effective on the long-tailed CIFAR-100 dataset with different imbalance factors. Here are some takeaway messages. First, we observe that different exits in dynamic early exiting networks are responsible for samples with different complexity at test time. Our intuition is that different samples should contribute unequally to different exits in training. Our proposed solution is sample weighting. Finally, a key design in our method is calculating the meta-objective of each exit only on its allocated metadata. Thanks for your time. Welcome to scan the QR codes to our paper and code.